diffusions. And the next talk will actually be jointly given by Molei Tao and Yuqing Wang. So I'll introduce both of them. Molei is an associate professor at Georgia Tech. He's worked on a wide variety of things, ranging from dynamical systems, optimization, deep learning theory, sampling, diffusion models. Yuqing is one of our research fellows. Prior to that, she was a PhD student of Molei's at Georgia Tech. And today, they're going to tell us about some finer grained theory about generalization and diffusion models that combines training and and sampling issues.
All right.
Take it away.
Thank you very much for the very generous introduction. So this is going to be a joint presentation with Yuqing Wang, just in case you didn't hear. I'll be focusing on like the high level part, and then Yuqing will talk about the technical part. And in fact, one disappointing fact is that 90% of the talk will be actually on the quantification of the generation capability of diffusion models. So this is generation, not generalization. And that means that at most 10% will be on generalization. And then you may say, let's kick this guy out. The reason that I'm still here is not because how much I like assignments, but it's more about that I have to go through the technical details in order to actually explain to you one of the interesting generalization settings. This is due to something called denoising square matching. So we have seen some discussion about it, and hopefully we can talk more about it. So this is something that I can say that we more or less understood. But then towards the end of the talk, I'll mention another generalization setting that we don't have much understanding of, and hopefully this can lead to discussions. To be fair, personally, we feel like the quantification of the generation capability is interesting as well. So hopefully you would agree with that as well. So without further ado, let me be more concrete. So we'll be talking about generative modeling. So the task is very simple. You guys probably all know it. You are given training data. I just want to generate more samples that are similar to the training data. And the reason that you can do it at a mathematical level is that you can assume that your training samples actually follow some underlying probability distribution, and then you are just sampling from the same distribution. You try to generate more sample from the same distribution. For example, you can be given like images of animal faces, and then you try to generate more images. The approach that we will be focusing on is called denoising diffusion model. It's currently arguably the dominant approach for generation of videos, of images, etc. But it's definitely not the leader in language models. So what it does is it basically uses like a two-step procedure. So there is something called noising process, forward noising process. Oh, I should have said that. So what is shown on the left is one instance of a data sample in your training data set, and then you try to generate new images that is like the one on the right. The way it does so is it uses a forward noising process where you just keep on adding noise to your data sample. For example, in terms of image, you will just get noisy and more and more noisy image till you actually get a total random image from which you can easily sample. So you sample IAD from that noise distribution, and then you try to revert the process. So you do that backward in time, and then structure miraculously emerges, and then you get a new IAD sample from the data distribution. So you may say this is impossible. You can't really invert diffusion. And the reason you can do so is here you're not just noising one image, you're actually adding noise to a collection of images. So you are effectively evolving a distribution of images. So along the way, you actually have an evolution of data density, and then you actually learn something called a score function that characterizes how this density evolves forward in time, and then you use that to sort of cheat and revert the entire process. More precisely, you can use a data distribution as the initial condition of some stochastic process. For example, a simple Orangena-Uhlenbeck process, or in fact any linear SDE would do. So you can use that SDE to push forward your data distribution to Gaussian if you run it for infinite long time. and then you try to revert the process. You try to revert the process by simply changing the sign of the time variable. So if you do so, the drift term is very easy to do. You just change the sign. And the problem is that when you try to change the sign of the noise term, you get basically the same thing because this is like a centered Gaussian random variable. You change the sign, you get the same centered Gaussian random variable in distribution. So this is not enough, and that's why you would actually need an additional term. So this red term is based on something called the score. So the score is actually something that is precisely defined. So if you define the score function to be the gradient of the log density of the forward process, then you can prove rigorously that the solution to the backward process is exactly the same as the forward process in distribution up to time reversal. Okay, so that's great. But the problem is, how do you get the score function? So like I said, it's something that you learn during the forward training process. Okay, so very intuitively, you may think, okay, so let's use a neural network approximation. So you use some parameterized function to approximate the score function, and maybe you can use this popular score matching objective function, where you basically try to put more emphasis on where the data is. And then you try to sort of solve this minimization problem, and then you can get an approximation of the score. In practice, of course, you have to do an empirical version, empirical approximation of the population version. So you have, say, little n samples in your training data set, and then you initialize your SDE using each one of them indexed by I, and then you get basically xi as a function of t, and then you just do this simple empirical average. But still, there is a problem. So the problem is you don't really know this score. You don't really know this density p. Otherwise, you are already sort of down. So this is not an implementable approach. But fortunately, there are solutions. For example, denoising score matching is one of the best solutions if you can make it to work. So what happens in denoising score matching is that you don't know this p, but you actually know a conditional distribution. So suppose you know the initial condition x0. Sorry. Suppose you know the initial condition x0. Then you actually know xt because you just solve a simple linear SDE. So you actually have the precise expression of this conditional transition probability. This is analytically available to you, so that's good. But then you do an expectation with respect to this conditional distribution, and then outside, you have to do more and more expectation with respect to your data distribution. Okay, so so you can actually prove that these two formulations actually give you equivalent minimizers. The proof is actually not trivial as it might seem, but it's actually doable. Okay, so this is a forward training process of diffusion model. Basically, you have to solve an optimization problem in order to get the score function. And then in the second step, you do basically something called a backward sampling / inference process, where you numerically simulate this SDE so that you evolve it from time 0 to time capital T, and then the solution at that time is basically your new samples. And then you can ask the question, what is the quality of the generated samples? For example, you can compare the distribution of x0, which is a training data distribution, with the distribution of y capital T, which is a generated distribution. You can use your favorite statistical divergence or metric, for example, KL is very popular. And in fact, this is a very important problem. There are a lot of existing results. The mainstream results are almost all like the following. So they say, if the score can be well approximated with some error, at most epsilon in some sense, then you can sort of quantify the distance between the generated samples and the training samples. They actually have statistical distance or divergence bounded by something under certain assumptions. Okay, so there are a lot of great results in this line. But in some sense, they only focus on the second part of diffusion model. So they assume that you already have an approximate score, and then they simply analyze the backward sampling process. To be fair, yes?
Sorry, when you say the samples have that divergence, you mean the distributions over samples?
Yes. Yeah, thank you. So to be fair, even doing so is highly non-trivial. And the reason is because you're not really looking at the exact backward dynamics, which would have no error, and it gives you exactly the data distribution. But in practice, you have all sources of error. Number one, you have score error, so this is really an approximation. Number two, you have to numerically integrate this stochastic differential equation. So a common approach is called an exponential integrator. So the idea is, okay, so y is the exact solutions. This is what you want. But you don't really have it because the score is actually a nonlinear function. It's represented by a neural network. And so you have to make approximations. You can't have the exact solution, but what you can do is you can discretize the time. So you can discretize it into time intervals. And then, for example, if your time is in between tk and tk plus 1, you just use the left value of the score function as an approximate equation, and then this becomes like a piecewise constant linear piecewise constant SDE, which you can analytically solve, and then the solution y hat would actually be a good numerical approximation of y. And you may say, I can do better than this. So in fact, how to efficiently integrate the backward dynamics is an active research frontier, or at least it was an active research frontier, because I mean this is closely related to how efficient your inference process is. You want it to be fast and accurate. One thing that people care a lot about is the number of function evaluations, because this S is parameterized by a large neural network, so its evaluation is very expensive. So if you do this exponential integrator, you just do one step, moving from one evaluation, moving from k to k plus 1 step. But you have to do many steps in order to go all the way from time zero in the backward dynamics to time capital T. So some of our approaches still are some of the best approaches after 2 years, 2 or 3 years. So what we can do is we can make the number of function evaluations to be about 10 to 20 for generation of high quality images. And people sort of believe that this is the limit of approaches that are based on numerical integration. So if you want to push this value further down, there are a lot of research in distillation, et cetera. So you do a lot of efforts offline, and then you can speed up the inference process online. That would be a different talk, so I will just say, let's just focus on the analysis of sampling based on this exponential integrator, as actually all theoretical results do. So that's integration error, and then you have initialization error. What is that? Okay, so ideally, you want to run the forward process forever and then revert it. So you want to initialize y0 at x infinity, which is Gaussian. But in reality, I mean, you have to take a value of capital T, otherwise you couldn't even evaluate. So you have to pick a very large capital T, but finite. And then ideally, you want to initialize the backward process at x capital T, because this way, the y capital T will be exactly distributed according to x0, which is a data distribution. But you couldn't do that because you don't really know the distribution of x capital T. So what people do in practice is they initialize at x infinity, because you know that it's Gaussian. But then you have some error. Okay, so you want to initialize at x capital T, but you only have x infinity. So there's some small error, some small discrepancy at initialization, which gets propagated through the backward dynamics. Okay, so you have to quantify that. I mean, that eventually leads to error in the generalization. And there's also something called early stopping. So the reason is because it's widely believed that you can generate very high dimensional data because the data actually has some intrinsic low dimensional manifold structure. If you believe that, then mathematically, your density is actually supported. The density of the data distribution is supported on some low dimensional manifold. The dimension is actually smaller than ambient dimension. And this creates a problem. So if you go in the normal direction to the manifold, then your density suddenly jumps from a finite value to 0. Which means that if you take the gradient of the density in the normal direction, you get infinity. So the score function, at least at time 0, is actually not defined. That's why in practice, people never simulate, well, almost never simulate this till capital T time. They stop a little earlier. They stop at T minus delta, where delta is very small. And then you have to change your accuracy quantifier. So you cannot compare x0 with yt anymore. But you can, for example, compare x delta with y capital T minus delta. And then you have to add something extra to sort of characterize, for example, how far away is x delta from x0. OK, so you have all those sources of errors, and the way you analyze their influence is dependent on what kind of data assumption that you make. So in fact, I mean, essentially, we're just trying to draw samples from a probability distribution. So this is a classical area. Prior to diffusion model and its analysis, there are already a lot of results. For example, so overdamped Langevin dynamics is very popular. So if you define the potential to be negative log of the data distribution, data density, and then you run overdamped Langevin dynamics, you are essentially just using a score at time 0. And then if you run this for a very long time, then your solution actually becomes distributed according to the data distribution. But how long? So it really depends on what kind of potential you have, which depends on what kind of data distribution you have. For example, so if your data distribution is unimodel, many times your potential would be M convex, and that would be a great situation. So the time it'll need is approximately at the order of 1/m to approximate the data distribution. But if you have a non-convex potential corresponding to multimodal distribution, then you have a problem, because the time it takes can be exponentially longer. If you contrast with diffusion model, the backward denoising diffusion process, the time it takes is always capital T. It takes capital T time to reach the data distribution. So in some sense, this is agnostic to multimodality. This is why one of the many reasons why diffusion model is preferable. It has less mode collapse when compared to, for example, GAN. And this is also in sharp contrast with Langevin, which suffers from multimodality. So what creates the difference? Well. So the main reason is because the score function that you have here is actually dependent on time. So you are actually chasing a time-varying distribution. You are shooting a moving target. And denoising diffusion actually corresponds to something called a annealing scheme, which corresponds to how you choose the moving target in a very specific way, so that it actually makes multimodal sampling efficient. And in fact, how to do annealed sampling is a very important topic. There are theoretical results as well. For example, some of the best researchers in this room actually have done great work, and some of the OK researchers collaborating with top researchers have, for example, done some recent work in quantifying, how good a specific annealing scheme is, given a general annealing scheme. Okay, so that's the ideal situation. So if you don't really think about errors, denoising diffusion is good in an almost obvious way, because it just reverts the forward process. So it doesn't care what kind of distribution you have. But in practice, of course, you have all sources of error. You have score error, integration error, initialization error. So characterizing whether you're still agnostic to multimodality is actually highly non-trivial. Basically, essentially, you care about, okay, how do those errors actually propagate through the Y dynamics, whether the propagation is in a controlled fashion or they actually accumulate and blow up. So the literature started with strongly log concave target distribution. So in this situation, your dynamics is sort of like contractive. So this is a relatively easy situation. Basically, you keep on forgetting about past errors. So errors don't really accumulate. But that's a very strong assumption. So people started relaxing it. For example, they assume that the target distribution satisfies something called isoperimetric inequality. It's basically like a perturbation to convex functions. If you look at the potential, so the keywords are like log-Sobolev inequality, Poincare inequality, etc. But still, that's just some relaxation of convexity assumption. And then people realized that we don't even need those. We just need like the data distribution to have bounded second moment. And also, there was assumption on the score function being Lipschitz, which is not a very good assumption because this is somehow a posteriori. So you don't really know this beforehand. And then people finally got rid of that Lipschitz condition, Lipschitz regularity. They really have minimal assumption, just the bounded second moment of the data distribution. For example, Benton et al. And Conforti et al. Both wrote nice papers about this. So they focus on different time schedules. So time schedules refer to basically like time steps that you use to discretize the backward dynamics. So the first one focuses on exponential time schedule. The second uses constant time, step sizes. They both focus on something called variance preserving SDE. What is that? So it basically means that your forward dynamics has to be this. So that it basically converges to something with fixed variance. So that's variance preserving SDE, but you don't have to do that. So in general, you can use pretty much any forward process. You can always write down the backward process as long as you have the score function. And in fact, a very popular version in the literature, for example, used by something called EDM, which is like the gold standard in the implementation of diffusion models. They actually use something called variance exploding SDE. So they basically remove this drift term, and then they just consider like a simple dynamics that keeps on blowing up your variance. And then you can also write down the backward process. This is a little harder to analyze. The existing results didn't analyze it. We actually do, but that was just a small component of our work. So we analyzed variance exploding SDE. And in fact, unlike the existing results, we actually allow arbitrary time schedules. The motivation is that we want to actually study how to choose my discretization so that I optimize my generation quality. So therefore, we prefer to leave this open and then optimize over it. So that was how we analyze the backward process. But like I said, that's only half of diffusion process, diffusion generative modeling. And in fact, there's a bigger component. So it's really about how you actually get a score function. So there's this forward training / learning process where you solve the optimization problem to get a score function. So personally, we feel like this is a bigger contribution of our work. We are actually the first one that do both. Okay, so the reason this is very important is because the quality of your generation largely depends on how well you approximate the score function. So like I said, the mainstream results all assume that the score function is given to you, but that's not really like the end of the story. Where does it exactly come from? So in fact, a score approximation is highly non-trivial, even if you know the target density, let alone in a generative modeling setup where you only have samples of the target distribution. And also, how you approximate the score function actually is pertinent to generalization, to really how well your model innovates. So this is actually an open question that I'll mention at the end of the talk. So we actually know where this comes from. I mean, in practice, it comes from an optimization. So let's start with the ideal denoting score matching objective. So this is a starting point, but it's not what people do in practice, because first of all, you have a time integral, so you have to discretize the time. Sometimes people say it's a sampling of time. Was there a question? Okay, sorry. And then people have to approximate those population averages by using empirical approximations, and then they have some empirical laws that can be optimized. To emphasize the fact that from now on we will talk about mainly, how theta changes as I do this optimization problem, and therefore I slightly change my notation to emphasize that theta is the optimization parameter. T and X are really just like input labels of your data. So this is the ideal situation just with S rewritten. We can further simplify it a little bit because we know the forward dynamics. It's really analytically solvable if X0 condition on X0. So for instance, you can write the forward the solution of the forward dynamics as a linear combination of your data and noise. So if you use variance exploding SDE, you can easily show this is actually going to be 0. And this sigma is what is called the variance schedule in the literature. This is something that is actually growing with time. So you just keep on adding more noise to your data. If you plug this inside the expression of, say, a conditional distribution, which is Gaussian, then the expression simplifies to this. And it's very intuitive. Okay, so what this score network is trying to do is you give it like a noised version of your data, and then it tries to spit out the noise itself, which is equivalent to like spitting out the clean data image, the clean data point. Okay, so this is why this training objective is called denoising score matching. It's really just doing denoising. This is also the formulation that we saw in the previous talk. And then you can start from there. You discretize the time. You can use your favorite quadrature rule. You have to introduce a collection of time grid points. These are called time schedule in the literature. And then you use an empirical approximation of this population average, and then you get like an empirical loss. Here, I simplified my notation a little bit because you have this chunk of things, but these are really hyperparameters that you chose prior to your training process. So in the literature, this whole thing is called the total weighting. It's another hyperparameter of diffusion model. And then up to this point, you have a minimization problem, and it becomes an art, how you optimize it. So the analysis that we will be doing is based on gradient descent optimization of it using constant learning rate. Okay, so we care about gradient descent training of this objective function. So in order to really do the full analysis, we have to actually parameterize the score function. So here we actually are parameterizing it using a wide ReLU neural network. Okay, so in the literature, in practice, people oftentimes use UNet or diffusion transformer. So these are extremely challenging to analyze. In fact, I mean, the ReLU neural network is also very challenging to analyze, but these are even harder. So I'm happy to tell you more offline. But basically, once you have the parameterization of the score, you have an optimization problem. Let me emphasize again, the optimization problem looks complicated. It has a lot of hyperparameters. So by doing the analysis, we would actually be able to not only gain understanding of the training process and then how diffusion model really works, but also we have practical machine learning implications. In particular, we will understand how to choose those hyperparameters. So at this moment, we have to become more technical. So the roadmap for the technical discussion is we will be mainly talking about like a non-asymptotic error bound of gradient descent optimization of this loss function. One interesting thing is that this thing is actually going to be bounded by a constant that is greater than 0. And that actually has a lot of consequences. This basically will lead to an interesting generalization setting, which you will hear momentarily. And also, because we have a non-asymptotic bound, which has like a rate of convergence, you may ask yourself, okay, can I make the convergence faster? It turns out if you want to do that, that basically tells you how to choose the total weighting hyperparameter. And of course, by the end of this optimization, you get an error bound of the score. And then you can use that error bound of the score to do the second part, which is the analysis of the sampling process, which is basically your inference process. And then you will be able to get a full bound of the generation quality. And again, this is something that you want to optimize. So if you want it to be very accurate, based on what you have already learned on the choice of the total weighting, you can actually get preference about the time, which is this, and the variance schedule. Okay, so this is how we can choose the hyperparameters. Okay, so I think I'll hand this over to Yuqing at this moment.
Okay, thanks, Molei. I think I made first do a brief recap. So if we have an image and we want to add noise, and eventually we will be pushing everything to a noise distribution. This is our forward process. And then here we will push from noise to image. And for this process, we do training. And the goal is to approximate the score function. And for this process, this is the sampling process. And the goal of this process is to generate new images. Okay, so we have already seen the objective function, and we minimize it by the gradient descent. So you don't have to take a look at all of these details, just memorize this is like the beta j. And we also denote the whole thing to be the f of theta ij, which is the individual loss. And this is the empirical loss that we used through the training. And for the neural network S, we use the deep ReLU network, as Molei mentioned. And this is in the following form, where for the input and the output, we use dimension D. And what's in the middle, the width of the network is M. And we denote this theta to be all of the weight parameters. Okay, and for the input data, if you take closer look at this forward and backward dynamics, you will see we actually have both the time and the state variables to be inputted in the network. However, we can actually absorb this time variable inside this state variable. So we only need to consider the following form, where this xi is sampled from the initial data distribution, the images. And here, this this sigma is the variance of the conditional variable, and this Cij is just the Gaussian noise. Okay. And this sigma bar is a monotonically increasing function of t, and it starts at 0, right? So you start at a pure image. So at time equal to 0, it is 0. Okay. And for the output data, it actually takes the following form. So it's negative Cij over this sigma bar. And recall, our sigma bar seems to start from 0. So when it's approximating 0, then our output data will be actually very large. And next is the number of samples. We denote this small n to be the number of samples from the initial distribution. So the number of images we use. And this is indexed by I. And this capital N is the number of time point for the backward and forward dynamics. So it's like individual time point through this dynamics. And this is indexed by J. Okay, so for the assumptions of our theory, I won't talk about all of them because it's a little bit technical, but I will comment that these assumptions are pretty mild. And they preserve the nature of the diffusion models. For example, here is a requirement for the scaling of this xi, which is the samples from the images. And we require the norm to be of square root of the order square root of d, where d is the dimension of this xi. So the reason is that, well, recall our input data is of the following form, where this Cij is the Gaussian noise, meaning the magnitude of this Cij is just square root of d. Okay. So that means if we are pushing from image to noise, then we hope eventually this noise will dominate. So that means our this xi should be at most of order square root of d. When we push it back to our data, to the images, we don't want our noise. So we want this data, the image, the xi to dominate. So that means the magnitude should be at least square root of d. So that is the reason why we assume this square root of d here. Okay. And next is the convergence theorem. So I will go through that. So it won't be, hopefully it won't be too complicated. So it's saying for any epsilon train greater than 0, there will be a very large integer such that when the width of the network is greater than this integer, then with high probability we'll have the following bounds for the empirical loss. And moreover, at certain iterations, we can control the empirical loss within this epsilon train error. And what I want to comment here is this is an exponential decay bound, where, well, here we take the product of k scalars, and what's inside the parentheses is actually strictly less than 1. It's actually strictly bounded by a constant which is less than 1. So if you take the product, then it will be an exponential decay. Okay. And another thing I want to emphasize is this term. So for this term, well, we can actually rewrite this empirical loss to be the sum of each individual losses. Recall, I defined this small f to be the individual losses of each data point. And then this J star, this I star J star is actually the index of the largest loss f at the S iteration. Okay. So that is saying if we want faster convergence, we actually want to maximize this term over all of the indices. And that means we actually want all of these losses to be equally large. Okay, so that can be summarized into the following corollary, where if all of these losses are close to each other, then our convergence rate, our empirical loss, can be upper bounded by these terms, where here we see this is maximized over all the possible J's. Okay. And then if we take a closer look at this condition, and recall this f of theta ij is defined to be some total weighting, some complicated terms denoted as beta j, the total weighting, times 2 norm squared. And let me make a claim here that this condition or this corollary will actually help us imply how we can choose the total weighting of the training objective functions. Okay. So let's first take a look at this term, this norm squared term. Since this sigma bar is a monotone function of t, and it will be 0 at time equal to 0. So if you push this sigma bar t to be 0, then this part will actually shrink, and you will end up getting the norm square of cos c, which is even if you train this network very well, this will still be a positive value, so it can never vanish. And at the same time, if you push this sigma bar t to be very large, then it can be proved that this part actually will also dominate, and here, the error here will also be very large. So roughly speaking, the shape of this term is like this, something like this. Okay, so then recall that we require these functions, these f's, to be close to each other, so that we have to choose this beta j to be inversely proportional to the norm squared term. Okay, so that means, roughly speaking, this beta will take this shape, right? It should be small when the sigma bar is small and when sigma bar is large. Okay. And if we check what is used in practice, the EDM paper, like Molei mentioned, is a gold standard choice of parameters. This is their shape of the total weighting. And it's pretty much like a bell-shaped curve. And for other total weighting functions used in practice, they're mostly monotone. For example, for this paper, this is the very first paper of the score matching generative diffusion models. And they use the total weighting to be 1 over this sigma bar. So it's like monotonically decreasing. It's completely different. And well, indeed, the performance of the EDM paper is much better than the other models. So that implies this bell-shaped curve is actually a preferable curve. And the takeaway message is that the theory actually match what is used in practice. Okay. So let me briefly comment on the proof of convergence. So the framework we use is the Allen et al. 2019, where they adopt the semi-smoothness plus the local strongly convexity of the neural networks. And the key of their proof is this part I marked in red. However, this strategy no longer works in the denoising diffusion models. The reason is that first, if we take a look at the output data, as the sigma bar goes to 0, this will actually blow up. So we cannot control the scale of the output data. So there's no way we can assume small output data. And also, for the diffusion models, the correlation between the data are known to us, right? We have Gaussian noise, so it is almost known to us. And this is, in some sense, a good thing because it can help us get rid of certain data separability assumptions used in their paper. Although these two things are not completely the same, we still need to design some other tools. But anyway, it can be overcome. Okay. And very roughly speaking, our proof is to derive high probability bound using some high dimensional geometry facts. Okay. And still the same theory. So let's now focus on this epsilon train. So before I comment on the epsilon train, let's just take a look at the properties of the denoising score matching objective. This L bar EM is the empirical loss that we used, and it's defined in the following we've just seen. And if we take the number of samples, this n, to go to infinity, then it will converge to the population version I write here. So ideally, we want to consider the score matching objective instead of the denoising score matching. It's like the difference between the neural network and the score function. But the score function is unknown. So we then consider the denoising score matching, and this term can be shown to be equivalent to this term marked in red, which is the same as here, plus some constant. Well, this is actually some negative constant, but anyway, this constant is independent of this neural network model. So what this implies, this is actually implying this term marked in red has a positive lower bound, right? Which means the population loss, this L bar, has a positive lower bound. Okay. And if you can still recall the convergence theory, this is saying, well, if we can use arbitrarily large network width M, then we can use arbitrarily small epsilon train to control our empirical loss. And moreover, if we take a closer look at this, this is saying, well, the empirical loss can be 0, but the empirical loss, as the sample size go to infinity, it will converge to the population loss, which is strictly greater than 0. So is there a contradiction here? And the answer is no. So we can actually have both of this empirical loss to be approximately 0 and the population loss to be positive. Yes? Yeah, that's a very, very good question. Actually, this is I would say this is the gap between theory and practice. We take the network width we take a very overparameterized setting. We take the width go to infinity so that we can consider everything in a NTK domain, so that it is easier for us to analyze things. But we don't have to use it this way. The problem is we actually don't know how to do the analysis beyond this NTK domain. Okay, so the reason is that, the reason is the overparameterized setting. If we fix this network width, then this conclusion is under the sample size n, which is much less than the network width, right? This implies that the sample size is bounded, right? Okay. And if we consider this conclusion, this is true when this n goes to infinity. So these two conclusions are under different conditions. So there's no contradiction. But the consequence of that is, well, if we denote this epsilon n to be the difference between the empirical loss and the population loss, then if the epsilon trend is small, then the epsilon n should be large. So that means these two terms cannot be simultaneously small. And recall, well, I think Molei didn't mention that, but anyway, so when we're considering the full error analysis, we track the KL divergence between the true density of P delta at time delta and its approximation. So this is bounded by the discretization error and initialization error, and these two terms comes from sampling. And then plus the score error, ES, which is determined by both the sampling and the optimization. And this ES is actually bounded by some constant times these four terms, where the first term we've already seen, this is just the epsilon trend. And also here this is the difference between empirical loss and the population loss, and also estimation and approximation error. Okay, we actually don't quantify these three terms, but it can be at least partially done in the following works. So the main message I want to say here is that we can really apply the regression generalization setting or tools to the new diffusion model settings. And what's more is some open problems. In the previous slides, we've seen that the epsilon trend plus epsilon n has a positive lower bound. That means this bound will never go to zero in any case. So is this true? Can we obtain a tighter analysis, maybe through some different decompositions of these terms? Or maybe we want to integrate the generalization into the optimization process? Or a more high-level question might be, is this network really approximating the score function? Can this error really be zero? This is what we don't know about. Okay. So about our full error analysis, I won't talk about the details, but just to give you an example. So this is under the choice of the EDM parameters. So roughly speaking, this is what our KL bound looks like. I will not talk about these details for sake of time. Okay. And for this ES term, like I said, this is based on both sampling and optimization, where we have an alpha j, which depend on the time schedule, this tj, and the variance schedule, sigma bar, and times this, like the score error terms. And this alpha j is different from the weighting that is used for the training objective. So the logic for this ES is actually, we first choose a total weighting function for the training objective, and then we will apply the sampling schedules to our training objective. Like we apply this tj and also sigma bar tj here. Okay. And next, I will focus on the two concrete schedules used in practice. And more precisely, I will talk about the theoretical implications of how we can choose between these two schedules. Okay. So the two famous choices of schedules are first, the Song et al. 2021. This is the first work for the variance exploding case. And the second work is the famous EDM paper. It has an improved design of the diffusion models. This Song et al., they use the time and tk. Well, you can take it as a function of k. So this k appears here. So it's just an exponential in k. Well, all the other parameters you see here is just chosen to be constant. Okay. And for this EDM choice, you can see this is a polynomial in k, where this row is chosen to be 7. And we mainly consider the following two situations when we want to compare the two schedules. The first situation is when the network is very well trained, meaning our neural network is pretty close to the true score function. So in this case, the exponential schedule, the Song et al. Paper, the very first paper, they will give us smaller error. However, if we consider the less trained case, meaning the score error is, the neural network is pretty far away from the true score, then the EDM version, the polynomial schedule, will give us smaller error. Right, okay.
All right, so I'm gonna summarize. First of all, we obtained the first quantitative result that analyzes the full error bound of the generation quality of diffusion model. We were the first result because we analyzed both the forward training process and the backward sampling process. The analysis of the training dynamics is rather non-trivial because we actually focused on some real neural networks, so it's over-parameterized, but in fact finite, real neural network. And also, because of the unique setup of diffusion model, our data assumptions have to be weaker, so we don't require separability of the data. We don't require unbounded, we actually have unbounded output labels of the data, so these are actually beyond assumptions that have been considered in the literature. There is an interesting generalization setting number 1. That's because really you try to do score matching, but you couldn't, and then you do denoising score matching. So at the population level, these two are equivalent, but at the empirical level, you start to see a gap. And the theory gives us a lot of understanding of what really is under the hood of diffusion model, but also it gives practical implications. In particular, the analysis of the training process tells us how to choose a hyperparameter of total weighting, and by combining that understanding with analysis of the backward process, we also know how to choose the variance and time schedules. Okay, so we started a little late, so I want to spend 3 more minutes talking about just the 2 of the future directions. So future direction number 1, it's a second generalization setting, so this is wide open. Well, this is, I mean, within an arm's reach, I hope. So the quantification that we have been talking about is we have been comparing the distribution of generated data with the distribution of training data. And then, as we have been discussing extensively, what if I have a stochastic parrot? What if I cheat and say, okay, I generate data just by uniformly drawing from the training data? And then you ask, okay, how large is this area? Is this error? So it really depends on what do you mean by the training data distribution. So if you think the training data distribution is really just the empirical distribution, then this quantity is basically 0. So you get completely accurate generation, but it's garbage. So it does not innovate at all. So like I said, the key is really like what you choose as a training data. So maybe you were assuming there is actually some underlying nice continuous distribution, and then your empirical distribution is approximating it. Unfortunately, when you do the training of diffusion process in practice, you usually start with like an empirical loss. So this is actually implying that you're actually dealing with the empirical distribution, which is the sum of Dirac's. So in fact, I mean, if you deal with sum of Dirac's as your data distribution, and then you do everything exactly, so exact score parameterization, exact density evolution, and then the forward dynamics basically pushes the density to actually Gaussian, and then the backward dynamics, if exact, will actually pull it back to the sum of Dirac's. So diffusion model is very well understood if you have everything exact, because in this case, you would actually be just producing a stochastic parrot. However, I mean, Dirac distribution is discontinuous. Sum of Dirac's is discontinuous. Neural network in most situations is continuous. So if you use a neural network to approximate your score function, you actually get, for example, this red sketch rather than the blue one. So in fact, you have all sources of error. So I just mentioned about score error, but you have additional errors, and they all together allow you to actually sort of effectively sample from a density that is not the sum of Dirac's, but actually corresponding to those yellow regions. And it is really, in some sense, like an inductive bias that we heard in the previous talk. In fact, I mean, this is something that that is very important. There are a lot of semi-analytical and empirical results centered around this. And our hope is by understanding the training dynamics and doing like tight analysis of sampling, you can really transfer like the generalization capability of neural network for regression to actually the generalization ability of diffusion models. So you can quantify the inductive bias. Okay, so that's the first future direction. A second future direction is even shorter. So there are a lot of people interested in discrete diffusion model at this moment because they feel like this is something that can add to the success of language model. So it's actually possible to do a similar quantitative error analysis as we just talked about today for continuous diffusion model. And this way, hopefully, it can tell us when what is discrete diffusion model good at, how does it differ from autoregressive model, and how to best deploy it. Okay, I want to stop here. Thank you for your attention.
Maybe in the interest of time, you can bug Molei and Yuqing offline, and we'll set up for the panel.